Okay, you can start. Thank you.
Okay, thank you very much for this possibility to give a talk here. Uh, so my report will be devoted to carbon nanotubes. Initially I am from Belarus Institute for Nuclear Problem, Belarus State University. And very recently I shifted to the Center of Physical Science and Technology in Vilnius, Lithuania. So my field of interest is electromagnetics, nano-optics, and metamaterials, and also terahertz ranges. So my talk consists of this several parts. They include types of carbon nanotubes, history of carbon nanotube discovery, potential applications of carbon nanotubes, characterization with Raman spectroscopy, electronic and optical properties, electronic separation of carbon nanotubes, their conductivity, and surface wave propagation. So there are several allotropes of carbon nanotube, including diamond, graphite, amorphous carbon, and single-wall carbon nanotubes. Single-wall carbon nanotubes can be considered as a strip cut out of graphene and then rolled up to form a seamless cylinder. The way of the graphene sheet is wrapped is represented by a pair of indexes here, N1 and N2. These chiral indexes describe a vector of rolling, C. Depending on the direction of rolling, we have different types of carbon nanotubes, and they could be metallic or semiconductor depending on this vector of rolling. These are typical images of single-wall carbon nanotubes. Typical diameter of the tubes is 1 or 2 nanometers, and the length could be several centimeters. So the very high aspect ratio of carbon nanotubes determine their strong electromagnetic interaction in terahertz and microwave ranges. Here is the picture of multi-wall carbon nanotubes. Low defective tubes here, they are straight, and high defective tubes, they are curved. The first transmission electron microscopy evidence of multi-wall carbon nanotube was reported in Journal of Physical Chemistry of Russia in 1952. Here is the images of these tubes obtained that time. This paper was in Russian, therefore it has not been noticed in the world. And only in 1993, the single-wall carbon nanotube were first reported in Nature, and after that, these nanoparticles became a very popular object of investigation. Carbon nanotube could be considered as a big molecule which is chemically stable, very resistant to ambient conditions. And it is quite strong and light, can be metallic or semiconducting, has low buckling force, has high specific surface area, has optical interband transition like an atom or quantum dots, and supports plasmon excitation and has antenna resonances in terahertz ranges. So carbon nanotubes has very interesting properties useful for different applications. Some of the application includes, for example, they can be used in medicine for drug delivery or thermolysis of cancer cells, in electronics. The films of carbon nanotubes, they are used as transparent conductive flexible electrodes, and the transistors and interconnects for energy storage. For example, in supercapacitors and batteries, carbon nanotubes are usually used as electrodes. So they can be used in solar cells, sensors, for hydrogen storage, in mechanics, as high-frequency oscillators and actuators. Carbon nanotube forests can be used as a field emission cathode. The dependence of the electron emission current versus applied voltage demonstrates the possibility of a room temperature emission of electron uh, at at not very high voltage. For example, emission occurs at 900 volts at room temperature. And for example, here it is presented the 1 millimeter square carbon nanotube based cathode for X-ray tube, which is only 3 centimeters in length. Another application is a chip for atomic force microscopy cantilever. Nanoprobes made of carbon nanotubes have high resolution, as their cylindrical shape and small tube diameter enable imaging in narrow and deep cavities. In addition, probe tip made of carbon nanotube have mechanical robustness and low buckling force. Low buckling force can be applied for imaging soft materials such as biological samples. So here you can see the scanning electron image microscopy images of motion of typical nanotweezers. Nanotweezers are a type of probe that is driven by the electrostatic interaction between two nanotubes on a probe tip. For example, this nanotweezer is open when the applied voltage is 0, and when applied voltage is more than 4.5 volt, nanotweezer is closed. So nanotweezers can be used for manipulation and modification of nanoscale objects and biological systems such as DNA. Here, there are example of carbon nanotubes, in how carbon nanotubes interact with DNA oligonucleotide. So this snapshot was a result of a calculation where we can see how DNA oligonucleotide penetrates inside the carbon nanotubes. So carbon nanotubes can be used as a carrier for drug delivery. The outer surface of carbon nanotubes can be immobilized with biocompatible materials, and inside they can be filled with the desired medicine. Such carbon nanotubes can cross the cell membrane and transport drug into the cell. Another possible application is a carbon nanotube as a ferromagnetic nanocontainer. They propose to put ferromagnetic material inside the tube for manipulation the structure with magnetic field. So together with ferromagnetic material, it's possible to put a sensor or drug inside carbon nanotube. So plasmid DNA by itself is unable to penetrate the cell membrane. So carbon nanotubes are proposed to use for transporting DNA inside the cell. Raman spectroscopy is actively used to characterize carbon nanotubes. The scattering of photons by phonons called Raman scattering. The scattered light has smaller frequency and can be detected. There is a resonant and non-resonant scattering. Resonant scattering is very strong, and it's possible to detect Raman signal from several tubes with lengths of 1 micrometer. High sensitivity of the Raman microscopy is used to detect distribution of carbon nanotube in the cells. Here is the optical image of the cell with the size of about 10 micrometer. Raman microscopy image demonstrate carbon nanotube distribution inside the cell. So now we will speak about electronic properties of carbon nanotubes. Periodic boundary conditions along the nanotube circumference leads to the quantization of transverse electron quasi-momentum. Energy band structure has several subbands in the conduction and valence bands. The electron transition between subbands with the same transverse quasi-momentum are allowed. Practically, semiconducting tube has two interband transition in the visible range, and metallic tube has only one interband transition. This electron transition can be observed in the absorbance spectra of the suspension with carbon nanotubes. Here, each peak in the spectra corresponds to the absorbance of carbon nanotube with specific chirality. Absorbance spectroscopy is a very good tool to characterize carbon nanotube material. In practice, the synthesized material comprises tubes of different chiralities. However, for more effective application, one needs to have tubes with specific chirality. So synthesized tubes should be separated. And one of the most reliable separation method, is density gradient ultracentrifugation. Tubes are covered with specific surfactant, then strong ultracentrifugation at acceleration as high as 1 million G for 10 or 20 hours applied. And as a result, carbon nanotube distributed in the gradient of density concentration, and carbon nanotube suspension with specific chirality has a specific color. So you can see here. Separated single-wall carbon nanotubes are available on market. For example, the price of separating 99% metallic tubes is rather high. So it is about $900 for 1 milligram. So approximately the same size for semiconducting nanotubes. So here a little bit formulas. Here I would like to remind you the derivation of Drude formula for AC conductivity in the metal. So free electron is exposed to the external impressed high frequency field. Equation of motion for electron is as follows. The solution of the equation we will look for in this form. As a result, we arrived at the current where the conductivity has a complex form, and imaginary part here, imaginary part of the conductivity is a result of electron inertia. So, namely, this part of the conductivity is responsible for the surface wave propagation in metallic carbon nanotube. Let us speak about the surface wave propagation along the carbon nanotubes. If we take, if we consider carbon nanotube as a hollow cylinder with infinitely thin walls and radius r and conductivity sigma, we will arrive to the following dispersion equation for the surface wave in carbon nanotubes. What is interesting here that radius of the tube is very small, and imaginary part of the conductivity is small as well. And if imaginary part is larger than the real one, uh, then uh, the solution of this equation gives us a wave number for the surface wave, and we can find then the phase velocity of the surface wave is very low. It is about 50 times less than the speed of light in vacuum. And this is very important, and I think to say that's unique properties of property of carbon nanotubes. And this surface wave, because of the strong retardation effect, this surface wave is strongly localized near the carbon nanotube surface. Here you can see the radial dependence of the axial component of the time average Poynting vector for surface wave of carbon nanotubes. So this surface wave is also called plasmon polariton wave. Here, the surface conductivity of carbon nanotube computed in the terahertz range, and tau is a relaxation time due to electron scattering by phonons. And in this frequency range, real part of the conductivity is less than the imaginary part, and namely in this frequency range, the surface wave can propagate in carbon nanotube with low attenuation. The first direct observation of the surface wave in single-wall carbon nanotubes using infrared scattering type scanning near field optical microscopy was reported in 2015. In the experiment, tube was located on the substrate. Tip scattered infrared radiation moved along the tubes. This tip excites the plasmon wave in carbon nanotubes, and this wave moved along the tubes and reflect from the ends and form the interference picture. And radiations due to the interference effect, plasmon excites the tip, and radiation scattered from a tip was measured. So in this way, it is they obtain this picture, and from this picture, it's possible to estimate the wavelengths of the surface wave in carbon nanotubes. And what they found that the wavelength of the surface wave is quite small, and if they study two tube bundle and three tube bundle, the wavelength is in this case is larger, and it is quantized. This is very interesting properties of carbon nanotubes because due to the very small surface wave length, the geometrical resonances for carbon nanotubes with lengths of about 1 micron occurs in the terahertz range. Here there is a formula, analytical formula for surface conductivity of carbon nanotube in the type found in the tight binding approximation. This formula take into account intraband transitions in carbon nanotube, intraband and interband transitions. And here is the spectra of the carbon nanotube conductivity in the very wide range, and this spectra can be divided in two parts. The low frequency part from radio frequency up to the middle infrared range. there is a Drude regime of the conductivity for metallic nanotubes. And in the near-infrared and visible parts, the interband transitions produce several resonances. And on the right side, you can see the experimental results for optical density of carbon nanotubes films. On the upper part, this films enriched with semiconductor nanotubes, and on the lower part, enriched with metallic nanotubes. We can see that the high frequency part, where interband transition occur, coincide and well described by the theory. And in the low frequency part, we can see the non-Drude behavior of the effective of the optical density of the tube. So there is a broad resonance in the terahertz range, and this resonance originates from the geometrical resonances of the surface wave in carbon nanotubes. So I would like to stress that the wavelength of the tubes is about 1 micrometer, and the wavelength in terahertz range is about 100 micrometer. So the wavelength is much larger of the wavelength. The wavelength of the light of the electromagnetic wave is much larger than the size of the tube. So a little bit how we theoretically model carbon nanotube-based composite. This modeling divided into 3 steps. At first step, we compute dynamical conductivity of single-wall nanotubes. We use quantum mechanical transport theory for graphene sheet rolled up in tubes. Once we know conductivity of the tube, we apply classical electromagnetic, we solve a classical electromagnetic problem of plane waves scattered by small particles. In this case, we can model carbon nanotubes as a hollow cylinder with infinitely thin walls, or as a prolate spheroid made of anisotropic material. So all this calculation gives us a polarizability of finite length single wall nanotubes. Once we know polarizability, we can, using homogenization approach, we can compute effective permittivity of single wall nanotube-based composite. If in the case when carbon nanotubes do not interact with each other, or we can, for example, neglect this interaction. In this case, we can use very simple Waterman-Ruel approach, where effective conductivity of the composite material can be easily calculated from the, if we know polarizability of individual nanotube. Okay, and here is the results of the computation of the effective conductivity of the composite comprising carbon nanotube of different lengths. So if the length of the tube is very large, in this case, finite length effect does not exist, and
Misha, you have 5 minutes.
Okay, this is the last slide. So, and here is the effective conductivity follows to the conductivity of individual tubes. And we can see that in the visible frequency range where interband transition occur, we have many interband transition, and the conductivity doesn't depend on the nanotube length. And in terahertz range, there is a regime where antenna resonances occurs in carbon nanotube. And in the low frequency quasi-static regime, Because of the strong depolarizing effect, the currents are suppressed in the tubes, and the electromagnetic response from the tube is small due to the screening effect. So, and in conclusion, I would like to repeat the main properties of carbon nanotubes. So carbon nanotubes is nanotube is chemical stable, the strongest and stiffest material, highly conductive, has low buckling forces, has specific surface area, can be metallic or semiconducting, has optical interband transitions, support plasmon excitation, and has antenna resonances in the terahertz range. So thank you for your attention.